Okay, thank you for having me one more time. So this talk is a follow-up from last year. We ran a workshop on natural language processing. It was an introduction for beginners. And this is a slightly more advanced topic, but in the same spirit. So it's also hopefully an introduction accessible for beginners. So word embeddings is the core topic of this presentation. In the title, I use word vectors, so that's already a little spoiler probably. So as a basic definition, word embeddings are vectors that we use to represent words. As a synonym, sometimes we see also semantic vectors to highlight that we use these vectors to represent the meaning of our words. And also another synonym is distributed representations to highlight that the meaning of a word is distributed across different dimensions. So why is this important? Long story short, in data mining, the way you represent your data is crucial for the success of your application. And similarly, in text mining, the way we represent our text is crucial for the success of our application. So word embeddings are really just an interesting way of representing our text. In terms of applications, anything related to text analytics is fair games for word embeddings. I'm just going to mention a few applications, but the list doesn't stop here anyway. For example, classification, you have a document, you want to label it according to the topic. That's one application of text analytics. And word embeddings have shown some interesting improvement in the quality of classification. Recommended systems, so you know how users can rate products and services, and they can also write reviews. So recommended systems can use the language in the review to improve the recommendations. Search engines, you type in your query in a search engine, and then the search engine is able to understand your information need and to expand the query to provide better results. And finally, I want to mention machine translation. So you have a piece of text in English, and you want to translate it automatically in French, Spanish, whatever, by means of a computer software. And in all these kind of applications, we have seen improvements in quality when using word embeddings. So word embeddings are really a representation for text that can produce interesting results for your end application. Now, introducing word embeddings, as we said, they are vectors. So here we have an example of vectors represented in 2 dimensions, but really, typically, we have 200, 300 dimensions for these vectors. And we call these low-dimensional vectors, low-dimensional compared to the thousands of words that potentially we have in a vocabulary. And we use word embeddings to represent also similarity between words. For example, here, Rome and Paris are similar concepts. So they're both cities, they're both capitals, they're both in Europe. So similar concepts, we want similar vectors, so they're close to each other. And also, Italy and France are similar concepts. They are both countries, they're both in Europe, good food, good wine, you tell me. So they should be close to each other. And what you see from this example, you can almost see a direction here from Rome to Italy and from Paris to France. So hidden in this model, we have a notion of a semantic relationship between these different concepts. The model doesn't really know about the relationship, but it is there. So the relationship of one being the capital of the other is hidden in this model. And this is basically the beauty of word embeddings. This is where all the interest about word embeddings is coming from. You can simply do arithmetics with vectors and look into this semantic relationship. So let's say you take the vector for Paris, you add the vector for Italy, and you remove the vector for France. You end up with a vector which is very, very close to the vector for Rome. So we are playing basically the analogy game here. You don't end up in Rome, you end up with a vector which is very, very close to Rome. We don't have vectors yet, we have language. So how do we go from language to vector? There is one main linguistic intuition behind it. This is called the distributional hypothesis. And it's nothing new. It goes back to the 50s. And to describe the distributional hypothesis, typically every talk about word embedding is making a reference to John Firth, a British professor of linguistics. 1957, he said, you shall know a word by the company it keeps. A couple of years earlier, another professor of linguistics came up with a similar notion. So words that occur in similar contexts tend to have similar meaning. Probably this is a bit less intellectual than the previous one, but it's also more clear. So in summary, the distributional hypothesis says we can approximate the meaning of a word by using the context, so by looking at what's going on around the word itself. Example, you have a sentence, I enjoyed eating some pizza at a restaurant. We focus on what's important, so that's our focus word, pizza. The idea is we can use everything else the company keeps to define the meaning of our word. So pizza is something that you eat, pizza is something that you have at the restaurant, pizza is something that you enjoy. Scale it up to thousands of sentences, and then once you aggregate, you have the deep real meaning of the word pizza. Counter example, you have two different sentences, I enjoyed eating some pizza and I enjoyed eating some Welsh cake. So these are our focus words, and for the sake of the example, Welsh cake is a single word. And maybe you see where this is going. We have exactly the same context, and according to what I told you so far, same context means same meaning, okay? So if you find this equivalence outrageous, blame the data. This is what the data set is telling us. Okay, that's the general idea. I want to introduce Word2Vec as an example of algorithm. So word embeddings are really a family of algorithms, and Word2Vec was the first one to generate a lot of buzz around the idea. So in 2013, a couple of papers were published by Tomasz Mikolov and colleagues from Google. And it was an academic success, but also they released the software as open source. And they pre-train some vectors on a corpus of Google News, so billions of words, and they released the vectors in dynamic, in binary form as well. So the idea about Word2Vec, we're looking at things from a distance. So at the high level, the idea is we want to learn these word vectors from our text. So first you choose an objective for learning. You initialize randomly, and then you run stochastic gradient descent until you reach the vectors. Now, if you've done machine learning before, you've seen something similar probably. You can apply the same pattern in so many different applications. So initializing randomly and then running some variation of gradient descent. So what's interesting probably for us is what's going on with the objective function. So the objective function, back to our pizza example, we have the focus word and we have the context words. So the objective for Word2Vec is to maximize the likelihood of the context given the focus word. When you see likelihood and given, you should think about conditional probabilities. So essentially, we're going to end up with a bunch of probabilities that look like this. Probability of observing a context word given the focus word. And the probabilities are related to the vectors, of course, and similar words should have a high probability. And that's kind of enough theory for a 20-minute talk. Now, moving on with a bit of practice. As I said, Word2Vec was popular academically, but also it was well received in the broader community because they released the software. The software was written in C, and here we care about Python. So we look into this library, which is called GenSim. The punline for them is topic modeling for humans. So what they do is they implement a bunch of natural language processing algorithms, and they stick a nice, easy-to-use interface, Pythonic interface on top of it. So if you do NLP, basically, look into GenSim, and you will find a lot of interesting algorithms, including Word2Vec and other word embeddings. So pip install GenSim, and we're good to go. I'll give you a quick example first as a short snippet. So you can import the class for Word2Vec. You have your data in whatever kind of format. And then on the third line, you have the corpus reader. That's the bit that you need to customize. So your corpus reader should be aware of the data format, and probably will do some pre-processing if you need to, and it will yield one sentence at a time. Now, because Word2Vec uses stochastic gradient descent, you don't need to load the whole data set in memory. You only need one sample at a time. So only one sentence at a time is needed. In Python, this means the corpus reader can be a generator rather than a list, for example. And then the final bit, you train the model with the Word2Vec class and then kind of hiding a few details. The Word2Vec class takes a bunch of arguments, so you can customize the number of dimensions, the size of the context, and a few more options. But this example as it is, as long as you write the corpus reader, works. So it's as simple as that. And the model, once it's trained, a few seconds if you have a small data sets, a few hours if you have a lot of data, will have all the vectors from our data set. So this is an example from a data set of CVs. So people write their experiences, their skills in the CV. And we are taking the vector for the word chef, and we want to see what are the most similar words to chef. So this is similarity between vectors. The numbers are cosine similarity, really. And you can see the most similar vector to the word chef is the word cook. In fact, they're synonym. That's fine. And then later on, you have bartender, waitress, restaurant, and more other words. These are not synonyms, but they're kind of related anyway. They belong to the same topic, so it all makes sense. Now, the word chef also has a different meaning. If you are a DevOps or infrastructure engineer, chef is one of the tools that you might use. So this is what happens if we do arithmetic with vectors. We take the word for chef, we remove food, so chef minus food. The result is Puppet, Ansible, Salt. These are all libraries in the DevOps space, so it makes perfect sense. What I found interesting here, the first time I saw this example, the word salt is related to food, of course, salt and pepper. But the model is kind of smart enough to recognize that we're talking about Salt, the library in the DevOps space. So that's very interesting. Different example, using this time the pre-trained vectors. So as I said, Google pre-trained the model on a corpus of billions of words coming from Google News. So we're talking about web data, general purpose English if you want. And Jensen comes with all the machinery to load up these vectors. It looks a little bit busy probably, but you simply have the key vectors class and then a load Word2Vec format function to load up the model from the binary vectors. So like before, you end up with this model which has all the vectors from our words. So let's play the analogy game again, just to see how the model behaves. This is kind of the hello world in Word2Vec that you always see. So king minus man plus woman. Just to see if you're still with me, feel free to try to guess. What do you expect? King minus man plus woman, queen. The answer should be queen, and in fact, that's the result. And the other vectors, they are the wrong answer, but again, they belong to the same topic, so they kind of go together. Here's the previous example, cities and countries. So Paris minus France plus Italy. Here we expect Rome. Now, something weird is happening. We have Milan as first answer. So what's going on here? Probably, as I said, the model doesn't know about the semantic relationship. So it's just picking up from the data. So probably, Paris and Milan, they are important centers for business. They are important centers for the fashion industry. So that's probably what's being discussed in the news. And that's what the model is picking up. More controversial examples. Now, professor is an interesting word because different from king and queen, we don't have different words for male and female. Okay, we have just professor. So professor minus man plus woman, a woman professor should be, again, professor simply. What do you expect? Teacher? We're still in academia. We're still in academia, but we have associate professor, so kind of one level below in the career ladder, if you want. And then further down, you have sociology professor, psychology professor, and so on. Now, you might object, in every career pyramid, you have more juniors than seniors, so maybe it's just a statistical coincidence. Associate professor is coming up more often. So now we can look at the same example in the other direction. So professor minus woman plus man, so a male professor, we expect, again, the result to be professor or maybe associate professor. Any guess? Professor? Super professor. So professor emeritus, one level up in the career ladder. So something dodgy is happening here in our data set. And we can play more controversial games. So computer programmer minus man plus woman. You can guess, but reality is going beyond your imagination. Go for a wild guess. HR, graphic designer, secretary. No. No. So clearly something weird is going on here, something wrong. And if you take nationalities and ethnicities in the picture, the language can get quite abusive. So that's the last example for in this direction. Where I'm going with this, so culture in general is biased, stereotypes and whatnot. Language is simply picking up from our culture. Language is a reflection of our culture. And then when people tell you we're using artificial intelligence for our decision-making process, so we take human bias out of the picture, the question should be, really? So in machine learning in general, the final product is always algorithms plus data. Okay? So it's not just algorithms. Algorithms maybe are biased, maybe they're not, but data usually are biased. So something to consider. Now, I started with Word2Vec because it was the first one to generate a lot of noise, and then it triggered a lot of work in this direction. So I just want to briefly mention a few other algorithms. GloVe is the first one that came out from Stanford. So GloVe stands for Global Vectors. They use an approach based on loading the co-occurrence matrix, so counting all the words that occur together. If you load the whole co-occurrence matrix in memory, you will need a lot of memory. That's what's happening with Word2Vec. Sorry, with GloVe. Now they propose some experiments. They show some benchmark where they improve the quality on some specific academic data sets. But in general, the sort of shared feeling in the community is that it doesn't make much of a difference for your downstream tasks. So you pay a lot for memory, you take a big hit in terms of memory, but you don't see a much, you don't see a big performance improvement later on. Another approach is called Doc2Vec. Now the name, of course, plays the same game. So we're going from vectors to documents. You can use vectors to represent documents. More in general, you can use this approach to represent any kind of a chunk of text. So sentences, paragraphs, groups of documents, whatever you like. The approach is essentially an extension of Word2Vec, so exactly the same, but for the conditional probability, you have an extra label at the end. The label is your sentence ID, document ID, whatever kind of ID you want to use to aggregate the probabilities. Otherwise, the approach is basically the same as Word2Vec. And then more recently, we had fast text. This one is coming from Facebook, same guy who used to work for Google, then moved to Facebook, and they developed fast text. Fast text is also an extension of Word2Vec. If you need to summarize it in a couple of words, it's Word2Vec plus morphology. Morphology means takes into account character-based bigrams and trigrams, so sequences of 2-3 letters within the word to enrich the model using the morphology of the word itself. What they did, they also pre-trained the vectors on a corpus of Wikipedia documents, not only for English, but for many other languages. Wikipedia tends to be a little bit less biased than Google News because it's more kind of a encyclopedic style, if you want. but also that's general purpose English. There's a good chance that your specific business domain is not general purpose web-based kind of documents. It works well if the type of language you're dealing with is morphologically rich. So English is not really morphologically rich. You see some interesting improvement in multilingual applications. Okay, wrapping up. As I said, distributional hypothesis, this is nothing new. It's been around for a while. There's been a lot of work in the context of working with co-occurrences. So counting words is nothing new. But what happens with the word embeddings is we're counting words in a fancy way, essentially. So we are creating a text representation that usually performs better for the downstream tasks. And also there's an aspect of scalability that I didn't include in the presentation, but still is there. You can scale up to bigger data sets using these word vectors. Machine learning, we have a notion of garbage in, garbage out. If your input is rubbish, your output will be rubbish. So using pre-trained vectors, I'm not saying they're rubbish, they're often useful, sometimes they're not. So if your business domain is not using general purpose English, probably they're not very useful. You just get started, you get a flavor of how we use the vectors, and then you need to train on your own data set. So business domain is very important. If you have a tiny, tiny data set, so less than 100,000 words, you probably don't see any benefit from using word embeddings. From 100,000 words, as a kind of rough estimate, you start picking up some of these semantic relationships. More than 1 million words, definitely train your own model. 1 million words is a small, small data set. So the summary of the summary. First time you look into word embeddings, looks like magic, but really, yes, unsupervised learning, artificial intelligence, whatever you call it, we're counting words in a fancy way. And if you don't care about the theory, JNSIM makes your life easy. It's an interesting library to check out. If you don't care about the theory, you might end up with those models with a lot of bias from their data. Okay, the slides are on my speaker deck. I circulate the link later, and if we have time for questions, I'm happy to take questions. Otherwise, we go for lunch. Thank you. Question at the back?
Hi, Marco. Thanks for the talk. When you were talking about you've got more than 100,000 or getting up to 1 million words, definitely not training your own model. Is there any advantage in doing some transfer learning? So the way that convolutional neural networks can take, say, the BGG network and some when they have, like, they're trying to train, so they take an inception model, they've got the architecture already, and then they train it. Is there any advantage to taking the words of that model as it exists and start using that as a starting point and then retraining it, like more bespoke for your situation? Is there any?
So can we use the word-to-vec model as a starting point for something else?
Yes, more specific to your domain area.
Specific to your application domain, task, whatever you're doing. The short answer is yes. The long answer is it depends on what you're doing. But typically, word embeddings are, because they're just vectors, you can use them as features for what's going on downstream. So that's perfectly fine. Typically, because they're neural network models, if you have a very small data set, that's not enough. You don't see anything interesting. So I tend to kind of roll back to rule-based approaches for that case. But 100,000 words is a very small data set. Let them in.
Thank you.
Yes?
Just wanted to make sure I get it correct. So when you do the subtraction between two vectors, then you notify the word in the search and you it somehow. So is that not computationally prohibitive? Is it like, it must take quite a while, right, to search all your word database to see which one matches?
Okay, so the question is when we do vector arithmetics and then we're looking for the most similar vectors, is it slow? That's typically relatively fast. It's quite fast, yeah. So the similarity is cosine similarity. Now JNSIM takes care of a lot of the optimizations that under the hood, so you don't worry about it. It's typically quite fast, yeah. and the arithmetics is just arithmetics between NumPy vectors.
Yeah, yeah. And one other thing, sorry, has anyone looked into this space, this like high-dimensional space that these vectors are part of? Like, you know, what is dimensionality? I'm just curious. And
Okay, what is the dimensionality? What's going on with the high-dimensional space? So, as a rule of thumb, 200, 300 dimensions is what people typically use. Less than 50 dimensions, it's not enough. You don't see these semantic relationships. More than 1,000 dimensions, you don't get any additional gain. So that's kind of a rule of thumb, and if people disagree with me, I'm happy to discuss. It's what people usually observe. All these pre-trained vectors, I think they are all from Google and Facebook in 300 dimensions. What you see as a broader comment in the space, you see similarity between similar concepts. So if you try to project using PCA or other dimensionality reduction, the global picture doesn't make any particular sense, but locally you see similar concepts, they're grouped together. So it's really just a feature representation for similar concepts. And then how you use downstream, anything, as I said, is fair game. We have more time?
We've got time for another question.
One more question? Yes, here?
What does it mean if a word has close correlation, extremely close correlation with some vectors, but not all others?
What does it mean if a word has extremely high correlation?
Extremely close vectors in one set of dimensions, but not in others.
Okay. What's the meaning of the dimension, and what happens if you have similar dimensions for some dimensions but not for others? Dimensions don't really mean anything in particular. Some people try to force a meaning into, with the king and queen example, this is the dimension for male, female, this is the dimension for royalty, this is the dimension for whatever. There's nothing like that. So dimensions are just dimensions, and you should look at them as an aggregation. So similar vectors are similar concepts. Similar dimensions alone don't necessarily mean anything in particular.
So you always look at the average of all those vectors together. You don't average the vectors, you
just look at the vectors in high dimensionality. Yeah, we good? Okay, thank you.